All right, so as promised, let's actually go ahead and take that exact same example and try to compute 2p, which is really just the sum of p with itself. So the overall process is pretty easy to do. The only thing that changes is that my formula for lambda is a little bit different. But other than that, it's a pretty easy process to look at. So here I'm not going to care about the q at all, so I'm going to just kind of cross that out. So in terms of formulas, I'm going to have x1 equal x2. So anytime I need an x2, I'm also going to take it as being that value 2. Same thing with the y1. So y1 and y2 are going to be identical, and they're both going to be identified as a 5. So I'm going to compute 2p, which is achieved by taking p plus p. Again, remember, if I wanted to compute 5p, it's going to be p plus p plus p plus p plus p. I think I said p 5 times there. But anyway, you're going to add p to itself 5 times and just kind of go on from there. A little bit later, we're going to be chatting about formulas for how to actually do this addition really quickly. So when I start computing 10,000p, I don't want to do 10,000 additions. There's going to be a much faster way to actually dive in. So for now, because p is obviously itself, I have to use the other formula for lambda, which is not any more challenging to work with. So I'm going to have 3x1 squared plus an a. So remember that a is that number right there. And then that's going to be divided by 2y1. Again, fancy division really is just going to be multiplication by an inverse. Things aren't terrible after that. Okay, so 3 times x1, which is a 2 squared, and then I'm going to add an a to it, which is a 7. All of that divided by a 2 times y1, which is 5. All right, so up on top, that's what? A 4 times a 9, and then I'm going to add a 7 to that thing. So what is that going to be? 19, I think. So I think that sounds about right. So 12 and 7 makes a 19. And then instead of the 10 on the bottom, I'm going to again record that as a 10 inverse up on top. Again, division here is actually multiplication by the inverse, and then I clean things up afterwards. So I need to know what is the inverse of 10. So here that's going to be this inverse mod command, and there's going to be a 10 and against an 11. And I believe that that's going to actually kick out the number 10. Just kind of fun is that number is itself its own inverse, which you can actually see because if you took 10 times 10, they multiply to make 100. And you know that 100 is then 99 plus 1, which is, 9 copies of 11 plus a 1. So 10 is actually its own inverse, so that's going to become a 19 times a 10. And if you multiply those things together and reduce mod 11, you should actually see a 3 emerge. There's actually a couple different ways you could compute that. I think in the notes I actually have the 19 reduced down into an 8, and then I took 8 and 10 and multiplied them to make an 80, and then reduced into a 3. Or you can just do the big multiplication and then reduced afterwards. At the end of the day, you're going to see that lambda value of 3 nicely emerges. So that's the only thing that's different than last time, is that I'm going to have a slightly different way to compute lambda. Then I go into the exact same structure that I had before. So I'm going to have my x3, which is lambda squared minus x1 minus x2. And then I'm going to have my y3, which is based off of x3. So there's a lambda x1 minus x3 and a negative y1. All right, so shoving all that stuff. So 3 squared minus x1, which is a 2, minus x2, which is a 2. And that's going to become what? 9 minus 4, which is just a 5. That's easy enough. All right, so over here I'm going to have a 3. And the x1, which is a 2, minus that newly constructed 5. And then subtract a 5 off as well. What is that? That's negative 3. So 3 and negative 3 is negative 9. And a negative 5 makes a negative 14. If I reduce that, so if I add 11 a couple times, that's going to become an 8. So what that tells me is that the sum of those 2 points, so if I'm going to have p plus p, what's going to happen is that emerges as the number 5, 8, which is cutely enough that value q that we had before. So hopefully you're starting to see that there's some kind of weird connections between some of these things, is that when I begin to do some arithmetic, I may end up at the other number. It's not immediately obvious that that should have happened, but it's one of these things that we want to exploit, that there are some funky underlying structures and some stuff that I can maybe work with, but hopefully there's a little bit of masking as to what's actually going on so that I can actually build a somewhat secure crypto system out of them. But there's all kinds of weird things that are happening here. If I want to just quickly cruise through the construction of 2q, I can do that as well. So it's more or less the exact same process. What I do have to see is that obviously there's going to be a different lambda. So the same a value, a different x1 value. Here we actually do see a number like 2 times 8 inside of my inverse. So if I compute that, I'm going to have a 16. Here you can use the inverse command with 16, or you can reduce the 16 down into a 5 and then do the inverse. Once you're at that stage, you can use all the properties that we have with doing arithmetic mod p, is that you can reduce and then multiply and then multiply, then reduce. As long as you're remembering to reduce at the end of the day, you're going to kick out the correct answer. Here we also see that kind of funky property that we end up getting its own inverse emerging. So you get the 5 and 5 inverse, which is actually, we know, going to be a 1. But if you just copy and pasted that as a block of code, it's going to nicely evaluate and then kick out this 1 as well. So in one of the activities, I'm obviously going to give you this process to try to construct this addition algorithm. You're going to want to build some object that eats in an elliptic curve, eats in a prime, eats in a couple points, and then returns the answer. So you just have to have this as a block and then have it just generate things as you go. So one of the nice things to see as we move through all this is that we know that there are going to be 10 entries in this elliptic curve. So we have those 10 things smattered across the top of this little grid, and they're scattered amongst the left-hand side. So we have this little bit here and that little bit there. And what we can do is we can build up our classic elementary school addition table. So if I want to compute what is the sum of p with itself, so you go p on the x direction and then p on the y direction. And what you can see is that if you add those two things together, you do in fact get this ordered pair 5, 8, which is the thing that we just got done computing. So we know that we have that thing in play. Likewise, if I wanted to compute p plus q, you get 5, 3. The thing I mentioned you trying to compute was trying to do the other direction, so go p or q times p. So you get those things to not matter the order that you actually do, which is good when you're building these addition tables, is that we can actually see these additions no matter which direction we're actually having them come into play, which is this idea that this whole process is all commutative, is that I don't care if you take p first or q first, they're going to kick out the same thing. You can also see that sometimes you can take some objects and add them together and kick out this identity, which we know should be things that are stacked on top of each other. So we have 2, 5. Well, the thing that's on top of 2, 5, or its reflection is 2, 6, because 6 is -5 mod 11. So you get these identities to emerge as well. So it's kind of fun to build up these giant addition tables. It's obviously a pain to do because there's a ton of entries. So you can lazily just create a giant array and then just export it as this table. And then it says, hey, look at how much work we've done. I did all this addition and all is great. So I may have you fill in one of these at some point in time. They do take a little bit, but they're kind of good practice to see all of this addition come into play and kind of do all of that stuff. So as we move into the next section, what we're going to be doing is we're going to be talking about an analogous version of a discrete log problem in these elliptic curves. Again, that's going to give way to a version of the Diffie-Hellman, but in elliptic curves. So once we have this discrete log, we can build crypto systems like that, and then again, begin looking at all of the underlying properties on how secure is this, are there nice attacks to this, are there nice collision algorithms, all of those kinds of things are going to be living in the next section. So now that we've kind of gone through the nitty-gritty of how to actually identify this addition, we can actually begin to apply it and actually do some cool stuff with it.